You're listening to B is for Blog and our interview with Manu Sharma from the Natural Capital Project. This is part 2 of 3 of the interview. If you'd like to listen to the entire interview, be sure to check out B is for Blog. And you can find us at BSINGH, number 8, number 3, .wordpress.com. Natural Capital Project seems to be working on a lot of different aspects of ecosystems. So in the beginning, we were talking about water, and you yourself are a water analyst. There are other models that are also being created, I guess, at the same time?
Correct. Currently, we've developed models for carbon storage, biodiversity, hydropower production, as you mentioned, water quality, avoidance, reservoir sedimentation, timber production, crop pollination. So we're covering a fairly wide sort of area. The models are all still in testing and developing, and we're still validating them in different areas to make sure they're correct. All these models are part of a single toolbox called Invest, and as I said, the toolbox itself is free. You just go and download it, and then once you load the toolbox, all of the models are within that toolbox, and you can make use of whatever models you want for the particular area under study.
That is pretty neat. And you have very kindly sent over some awesome graphics of what the software that you guys are developing essentially actually looks like. So do you think you could just walk me through it?
Yeah, so one of the models we're working on is the water quality model, and it's based on the nutrient retention service provided by various types of vegetation. So for example, when it rains, rain mixes with pollutants and they travel across the land towards the stream. Now, as these pollutants travel, they encounter different types of soil, plants, and vegetation. Now, each plant and vegetation has a unique ability to retain some of these nutrients, thus helping to reduce the net load reaching a stream.
So when I hear that, the visual to me is it's raining, there's a forest or some sort of wooded area next to a stream. Actually, I live next to something like that. I live next to the Don Woods in Toronto. And the Don Valley River is right down there. So maybe at least the visual to me when I hear you say that is something along the lines of like those trees or that wooded land is essentially acting like a protective barrier for the river below.
Exactly, it's retaining some of the nutrients that are passing through it. If that forest was removed, you'd no longer have that retention service. For example, if they paved it, all the nutrients would flow right into, all the pollutants flow right into the stream. So it's very important. So we're trying to quantify the importance of that forest, for example. So the model itself is built of 3 scripts. The first script is the water yield script, and this is where we first model the hydrologic regime of the area. So essentially, when it rains, what happens to the rain as it flows across the ground, through the ground, into the stream. The second model, or the second script, is the nutrient retention, which models how the nutrients are retained and exported throughout the landscape. And the third is the actual economic evaluation script. Now, the actual valuation depends on the use of water in the stream, so for this particular case under study. So for example, if the water is being taken from the stream for drinking, then the valuation will be based on the avoided treatment costs associated with keeping that particular plant type. So for example, if keeping an acre of forest helped reduce the net nitrogen load by 20%, that saved us X amount of dollars in treatment costs. Okay,
cool. So let's pretend like I would drink out of the Don River. We can't because it's just so polluted. But anyway, so for instance, the value of the trees in this little wooded area in helping to make sure that water is clean.
Exactly. So if, for example, it costs X amount of dollars to treat the water, to bring it to a certain acceptable drinking water level. If you were to remove that acre of forest, that cost would go up because you have more nutrients reaching the stream. So because you have that forest there, it's helping retain some of the nutrients and thus reducing the load and thus reducing the cost of treatment.
Very cool. So what are the next 2 kind of images in this slide that's coming up?
So on the left is the nutrient retention map, and it basically highlights areas of high retention in the landscape and low areas. So in this map, for example, green areas indicate high areas of nutrient retention. So a policymaker or a land planner would focus on these areas and they make sure these areas remain intact because they're providing a very essential service. And on the right, there's also evaluation script. An example, purple in this case indicates high areas of value. So you see how there's correspondence between green areas on the left and purple areas on the right.
Awesome.
So these are the type of maps we're trying to develop.
I have to say, I also enjoy the colors. It makes it really easy to understand that way too. I have some basic science understanding, but you know, it is nice to have a good healthy visual. So I'm really glad that that's like a part of the project as well.
That's really why we're using spatial data sets and developing maps, because really numbers are one thing and text is one thing, but visualization is very important too for understanding things. And with maps, they convey the message a lot easier than text and numbers.
Awesome.